Are you looking for stable sorting algorithms in C#? You've come to the right place. C# doesn't have a lot of built-in options for stable sorting. In fact, Array.Sort, List.Sort, and even the newer Span.Sort are not stable. The only built-in stable sort, as far as I know, is link's order by. However, link has some disadvantages that make it impractical for certain situations. Specifically, link doesn't sort in place. It always generates a new sequence, leaving the original collection unchanged. If that's not an issue for your use case, then order by is a great alternative. Otherwise, you'll have to rely on custom implementations. With that in mind, I built a small library of stable sorting algorithms, no dependencies, unit tested, open source, available on GitHub. Link in the description below. Included algorithms are Insertion Sort, Binary Insertion Sort, using rightmost binary search, otherwise it won't be stable, MergeSort, a hybrid sort combining merge and binary sort, using merge for large datasets and binary for small ones, and what I'm calling Timsort Lite, which borrows a few ideas from Timsort for a slightly more optimized hybrid sort. Like I said, the code is available in the repository linked in the description, specifically inside the runtime/sort folder. Some of these algorithms also use binary search, so you will also need the runtime/search folder. If this is all you wanted to know, feel free to get the code from GitHub and close the video now. Otherwise, let's take a deeper look at these sorting algorithms. If you've stumbled upon this video and you don't know what a stable sorting algorithm is, I will explain. In a stable sort, if there are elements that compare equal, the algorithm keeps them in the same order relative to each other that they appeared in the input. Whereas in an unstable sort, those elements will essentially be placed at random. Again, relative to each other. This might sound a little confusing, but it's easy to understand with an example.
There's a nitpick I want to mention because it's relevant for selecting the sorting method, and that's stable sorting. I want to just show an example application which wouldn't work with an unstable sorting method. Suppose you have these Simpsons characters, first name, last name. You want them in sorted order by last name, and among those with the same last name by first name. And you could do the following: sort them by first name, and then sort them by last name. And you would hope that after that, all those with the same last name still have their first name in order. For this second sorting step, this would only work with a stable sorting method.
The structure and API of the algorithms in this library are all the same. There's a main sorting function that operates on a span and receives an iComparer. There's an overload that just uses the default comparer. And then there are multiple overloads for arrays, and these are really handy if you want to replace any usage of Array.Sort. You can literally just replace any calls to Array.Sort with Insertion Sort.Sort or TimsortLite.Sort, and it will just work. The API is exactly the same, with the same parameters and the same overloads and everything. All algorithms also have a version that operates on an iList. This version is always going to be slower than the span version, so if your data can be converted to a span, you should use that. However, I wanted this to be flexible, so providing an option for iList, which is the most basic contract you could have for a writable index-based collection, seemed like a useful addition. Hopefully this covers pretty much all use cases, since anything that can be sorted will most likely either implement iList or be convertible to a span, or both. Let's take a quick look at how these algorithms work. For insertion sort, we have a temporary x variable, and then two indexes that we are keeping track of, I and j. Everything is easier to understand with an example, so let's imagine we are trying to sort this sequence 6385. We start I at index 1, and we consider everything that comes before I as already being sorted. So in this case, everything that comes before I is just one single number, and we consider a sequence of size 1 as being sorted by default. That's why we start at 1. We make j equal to I, and we store whatever is at that index in our temporary x variable. Now we compare j minus 1 to x. Is 6 larger than 3? Yes, it is. So we copy it over to index j. We move j back one position, and since we're at the beginning of the array and there's nothing before it that we could compare against, we determine that the correct position for 3 is at index j, and we write it to that index. Now we move I forward one position, we set j equal to I, and we copy 8 to our temporary x variable. We compare j minus 1 against 8. Is 6 larger than 8? It is not. That means 8 is already at its correct position, so we don't need to do anything else here. We move I forward one position, set j equal to I, and store 5 in our temporary variable. We compare j minus 1, which is 8. Is it larger than 5? Yes, it is. So we copy 8 over to j, and we move j back one position. We compare j minus 1, 6. Is it larger than 5? Yes, it is. So we copy that over to j again, and move j back one position. Now we check, j minus 1, is 3 larger than 5? It is not. That means the correct position for 5 is at index j. So we write it to that index, and we are done. Since I is already at the last position of the array, that means everything is sorted. Binary sort is almost the same thing, except when we are trying to find the correct position for x, instead of comparing it against every single other element that came before it, instead we use binary search to make finding the correct position much faster, even though when we do find that position, we end up having to shift every other element in the array exactly the same way as we were doing with insertion sort. However, this still makes binary sort much faster than insertion sort in almost all cases, especially when the comparisons themselves are expensive, for example for strings, because binary search causes the algorithm to have to do way fewer comparisons. Once again, with an example, everything is easier to understand. So let's start from here, where we've already sorted everything except for the last element in the array. Otherwise, we won't really see a difference in binary search. And even here, when the array is so small, we can already see a slight improvement by using binary search. So we are starting with x being 5, so instead of comparing 8 and then 6 and then 3 against 5, instead, we start at the middle of the already sorted sequence. So we start at 6 and we compare it against 5, and if it is larger than 5, that means we need to keep going to the left. So now we compare 3 against 5, and if it is smaller, which it is, that means we have determined that the correct position for 5 is at index j. So we only had to compare 2 numbers instead of all 3. Now that we found the correct position for 5, we still have to move every element over. So we will have to move 8 over to where I is, and 6 over to here, and finally we write 5 to its correct position. So we still have to move the elements just as much as regular insertion sort, but finding the correct position was slightly faster. For merge sort, we start by recursively dividing our data in half until we have something of size 1. Actually, it would be size 2, because when we get to size 1, this is not going to do anything. So when we reach the smallest data size that we can, we start merging with this merge algorithm. So we merge everything that is size 2, and then everything that is size 4, and then 8, and etc, etc. So the bulk of the algorithm happens in this merge function. So let's see how that works. So we divide our data into 2 halves, the left side and the right side. Traditionally, this algorithm actually uses 2 temporary arrays, one for the left and another for the right. However, if we are a little bit more clever and we understand how the algorithm works, we realize that we actually only need 1 temporary array. Because yes, even though we are overwriting over some of the data that we need to compare against, we won't be overwriting all of the data. So only the left half needs to be set aside, because the right half will never be overwritten. And this will become clear when we look at the example. So here, once again, we keep track of two indexes, I and j. I is the index in the left side of the data, and j in the right side. And then we also keep track of an additional third index, which will be the index that we are writing to. So we check the first element of the left side of the data, and we compare it against the first element of the right side, and whichever one of those is smaller gets written into the first index of the data. And then we compare against the other two elements, and so on and so forth. So once again, let's take the sequence 6385. And the first thing that the algorithm does is split this data into halves, and then for each of those halves, it splits it again, and then these two are put through the merge algorithm. So 6 will be copied into the left temporary array, and then we need the variable k as well. I will keep track of the index in the left array, j will keep track of the index in the right side of the data, and k will keep track of the index where we are writing to. We compare I and j and check which one is smaller. In this case it's j, so we copy that over to k. Now we reach the end of the right side of the data, so we just copy whatever is left of the left side to those positions, and in this case it's just one single element, so this is now sorted. And the same thing happens for the second half, so let's just put those two in their correct position so that we get to the interesting part where each sequence actually has more than size 1. So now we have these two halves, and these two halves will be put through the same merge algorithm. So now we copy over the left half into the left temporary array. J will begin at the first element of the right side of the data, and I will begin at the first element of the left side, and k at the first element of the whole data that we are trying to sort. So we compare the first element of the left with the first element of the right, and it just so happens that the left element is smaller, so it would be copied over to this position, even though it is already the same value. So I increases by 1 position, and k as well, and j stays in the same place because we didn't use this element yet. So now, once again, we compare the left side at index I to the right side at index j. J is actually smaller, so we copy 5 over to here, and j bumps over 1 position, with k moving forward 1 position as well. Now we compare 6 and 8. 6 is smaller, so it gets written into position k, and at this point both I and j are already at the end of their respective halves of the data, so that means we are done, that everything is already sorted. For merge binary sort, it's going to be almost the same thing as regular merge sort. This part here at least is literally the same thing, with the small difference that whenever the size of the data is smaller than a certain threshold, in this case I chose 64 because it seemed like it was performing very well in my testing. So when the length of the data is smaller than this threshold, instead of using the regular merge sort algorithm, we use binary sort, because binary sort tends to be very fast for small data sets. So we kind of get the best of both worlds here. And for Timsort Lite, we also use a combination of binary sort and merge sort. However, the manner in which we decide when to use each one is slightly different than the previous algorithm. As the name implies, we borrow some ideas from Timsort to hopefully make this decision a little bit more optimized. The first difference is that instead of having a fixed threshold, we calculate it. Honestly, don't ask me how this calculation works because I don't really understand it myself, but I copied it directly from Python's implementation of Timsort, which is the most well-known and well-documented implementation of Timsort in a popular language. After calculating our threshold, we split our data into multiple chunks of the size that we just calculated, and we sort them using binary sort. And then we merge each of those chunks using MergeSort repeatedly until all of the data is sorted. So let's say our threshold ended up being 32. We split our data into multiple chunks of size 32, which we sort using binary sort. So now we end up with multiple chunks of size 32 that are sorted, and we run them through MergeSort in pairs. We will merge the first 2 pairs of 32 elements, and then the next 2 pairs of 32 elements, etc., until we end up with multiple pairs of 64 sorted elements, which we also then merge to end up with multiple pairs of 128 elements, and so on and so forth, until all of the data is sorted. And that's why we say here that we merge them in powers of 2. You may also be curious to know how these algorithms perform in relation to one another. So I've done some testing in the Unity profiler. If you're new to the channel and you're coming from the pure .NET world, just be advised that I'm using this for game development in the Unity engine. So the performance characteristics of what you see here might be different from Microsoft's .NET, even though I would be quite surprised if the relative positioning of each algorithm was significantly different. It's just something that you should be aware of. The tests were ran in a build compiled with IL2CPP, and each test ran for a total of 500 frames, and then I used the Profile Analyzer tool to calculate the averages of each function across those 500 frames. So the first test that I did was an array of size 500, actually 2 arrays, one with a reference type, this item that I'm testing here, and another with just integers. Important to note that items have a name and they are sorted alphabetically by comparing their names against each other, and that's actually the biggest factor in making them slower to sort than ints. As you can see, Insertion Sort is a clear outlier. It is much slower than every other sort by quite a bit. However, you should know that when arrays are of small size, let's say somewhere between 10 and 30 or 60, then Insertion Sort is really fast. However, Binary Sort still tends to be faster than Insertion Sort in basically all cases. But when arrays start to get into a relatively decent size, then Insertion Sort definitely starts to take a hit. Other than that, it is interesting to note that for the test item reference type, Array.Sort was the second slowest, followed by MergeSort, BinarySort, and then the MergeBinarySort hybrid, and then Timsort Lite. For an array of ints, the story is very similar, except the default array sort actually is the fastest one, where for the reference type, the default sort was the second slowest. So like I said at the beginning of the video, by the way, array sort is not stable, so in a way it's not really fair to be comparing these sorts against it, but it's useful to have an idea of how they compare against the built-in options. The next test that I did, I increased the size of the array to 1000, and I removed the insertion sort from the test because it was being a clear bottleneck. And now the story is very similar to what we saw before, array being the slowest one for the reference type, followed by binary sort, merge sort, and then the merge binary sort hybrid, and Timsort Lite being basically tied with merge binary sort. It's so close that you can't really say that one is faster than the other. And for the array of ints, the story is pretty much the same thing as it was before. Same ordering for the custom sorts, and array sort being actually slightly faster than all of them. And lastly, I tested with an array of size 2000, and the story is very similar to before, nothing really surprising here. However, here we see that binary sort is starting to lag behind a little bit, because the array is starting to get a little bit too big for what binary sort is really good at, which is small data sets. So the default array sort actually ends up being slightly faster than it, and then MergeSort. And here actually Timsort Lite appears before MergeBinarySort, but once again, the difference is so small that you can't really tell which one is faster. And for an array of ints, basically the same thing, once again with the default sort actually being slightly faster than the other ones. But yeah, nothing really surprising here, just something useful for you to have an idea of how these algorithms scale. Honestly, the only ones that you should consider using are Timsort Lite and MergeBinarySort, because they literally combine the best of both worlds. Whenever the data is large enough for it to matter, they use MergeSort, which is a lot faster on large data sets, and whenever the data is small, they use BinarySort, which is really fast on small data sets, so they really give you everything that you could possibly need.